right? So the time this guy takes to take, this is the dilated time, okay? And dilated just means bigger, okay? This distance is going to be twice the square root of d squared plus L squared over c, right? So now it's the hippopotamus of this guy, right? It's d is here and L is here, right? Okay. And this distance is 2L. And now we've got, now we can substitute something. It's not going to be prettier, right? But this is, so if it says fill out the derivation, right? And by the way, years ago, like 2 years ago, they basically had students on the IB test, and I'm sure that like 1 in 100 actually did it. They had them derive time dilation. Here, derive it. It's like, really? Okay. So let me just show you how you can blunder into this thing, right? And if you did this in 1905, you would have gotten a Nobel Prize, which I think is, on the face of it, pretty good. So what I'm going to do is I'm going to substitute. I know that my velocity here, the d is, or L is, what is it? It's 2. L is v. Oh, I know what it is. Yeah, this distance here is the velocity that the ship is going times the time divided by 2. That's what L is. Yeah, that's how we get into it, right? Okay. So L is the velocity times the time divided by 2. Velocity times time would be this whole distance, right? But L is vt over 2, right? So I'm going to make that substitution. T is 2 square root of d squared plus, and then I can go v squared t squared over 4, right? So I just substituted vt over 2 for L. Yeah? And now we've got a problem because we've got a formula for t in it that's got t in it. Generally, that's not good form, is it? Right? So let's get rid of that. I think what we do is we go, I think we square both sides, don't we? So we go t squared is 4d squared plus b squared t squared.
That becomes 4d squared plus 4d squared.
Waiting for it? Yeah, the 4's cancel, right? So I did two things. I squared both sides, and then I distributed that guy. Is that all right? And then I think what we want to do is take these guys and go t squared 4d squared over c squared, right? Right? In the formula, the formula's got like a v squared over, or a v squared over c squared, right? So we're getting close there, right? Okay. What do we do now? I think we want to get the t's on the same side, don't we? I'm thinking that's a wise thing to do, isn't it? Okay, so I'm going to say t squared minus v squared over c squared, right, equals, yeah? And then don't we factor out a t squared? Now it's looking pretty good because I know the formula's got a 1 minus v squared, right? Okay. Can't I just stick this in the denominator? We're almost there, right? I'm going to run out of space. Do we just square root now? I think we do, don't we? So t is 2d over c over the square root of, this is the dilated time. This is the time it takes that moving clock to tick, right? What is 2d over c? Is that the proper time? Oh my gosh. Holy derivation, Batman. Okay, so here's what we have, right? We've got that the dilated time is the proper time divided by the square root of 1 minus v squared over c squared. Ba-ba-da-da. Hallelujah, 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 hallelujah. Oh, sorry. So what does this mean? This means that, isn't this thing become less than 1? Doesn't it become less than 1? Yeah. If we're not moving, this is the square root of 1 minus 0, and therefore the time is the proper time. Huh? And then as we move, this time gets more and more because we're taking the proper time and dividing by something less than 0, right? And in fact, what happens if we go the speed of light? If we go the speed of light, then we have the speed of light squared over the speed of light squared. 1 minus 1 is 0. The square root of 0 is 0. Anything divided by 0 is infinity, right? So as something approaches the speed of light, the time it takes their clock to tick approaches infinity, right? Their clock slows down and stops, right? Or as Stephen Hawking says, if we throw somebody into a black hole, okay, or as we say in academic circles, if we were to have a graduate student jump into a black hole, right? Okay, we would see their hands, all their gesticulations as they head into that thing. They're going to approach the speed of light. Okay, they're speeding up and going faster and faster as they approach the event horizon. They will approach the speed of light, and we will see them wave slower and slower, and then eventually just freeze in motion. Right? We don't see them actually go into the black hole. But then they sort of fade out. They turn redder and redder, and there we have it. Right? Okay. So this is well, they would, pretty much just do anything they want for. Yeah, that's right. Okay, this is called the Lorentz factor. This thing, and so in your physics text, they just give the formulas the way that you normally would, but in this case, they actually give the formula. If that's the Lorentz factor, they give that square root of 1 minus v squared over c squared. They put that in the denominator, and the Lorentz factor then becomes this thing that instead of getting less than 1, actually gets to become more than 1, right? And so if you graph the Lorentz factor for this factor of the speed of light, so here's 1 times the speed of light, right? You can see basically what that does is it sucks it right to this asymptote like that. The fact that it's the square root of 1 minus v squared over c squared pulls this guy in like this. And if you're at half the speed of light, right, really the error looks to be only about 20% or so. At 0.2 the speed of light, it exceeds the ability of this display to show the difference. There's a very small difference. So you can go all the way up to about 2/10 the speed of light and pretty much ignore relativistic effects. This is why we don't really notice it, right? It's not like you drive to school and you go, oh, okay, I got to reset my watch, Okay, we don't really notice this at speeds that we normally go because it really only kicks in at really, really high velocities. Now, suffice it to say that we take particles and we speed particles up to these speeds and we notice that they decay slower, right, at these speeds. So this sort of thing, we've got very strong and good scientific evidence. We can take muons, speed them up to close to the speed of light, and they take longer to decay on average, right? So it's not like pie in the sky theoretical. I think when I was sitting where you are, I was like, I must resist to what the evil teacher is showing me. But just, keep in mind that this is all very well experimentally confirmed.
So would a clock on Mercury then keep going?
Yeah, it's going to tick slower for a number of reasons, right? One is that it's close to the sun, and the sun is this massive object, and massive objects slow it down. It's also moving, right? Yeah, so I mean, think about that. If you're in an airplane circling the Earth or a satellite, right? That clocks on satellites are going to slow down because they're going 18,000 miles per hour, a little bit, right? Now, is a satellite an inertial frame of reference? Is it moving at a straight line at a constant speed? No, it's accelerating, right? So that's not really a paradoxical thing. That's not a way to tell whether you're moving or not, because you're not obeying the first postulate, right? So if you look at the data packet, they give the time dilation formula this way. Times the Lorentz factor is that little gamma thing, right? Okay. That's the same as that formula. Put that in your mind, right? Do a little text substitution in your brain, right? I like that formula better, but this is the way they're given to you in the IB packet. Okay. The book